So I actually finished the discussion of all the properties, but it happened to be that somehow the recording equipment only record when I finish the discussion on the property 11, right? So actually property 10, right? So let's start the property 11. Okay. Orthocenter is in center of the pedal triangle. For all inscribed triangle in an acute triangle, the perimeter of the pedal triangle is shortest. So we can draw the figure first here. Let's call it A, B, C, right? And we know that we're talking about the pedal triangle. So this D, E, F are the foot on the three edges, the foot of the altitudes on the three edges. And we want to prove that orthocenter is in center of the pedal triangle. Pedal triangle is a triangle DEF. Okay. So we already know that CF is perpendicular with AB, AD is perpendicular with BC, and B is perpendicular with AE, right? So we know that this is 90 degrees, this is 90 degrees, this is 90 degrees. That is saying EHDC are cyclic. So this angle equals to this angle, right? And this one also equals to this one, right? We already proved these properties before, so we just use it here. This one equals to this one equals to this one, and this one equals to this one, right? Because F, H, D, B are cyclic. So this angle equals to this one, so angle FDH equals to angle EDH, right? And because FHDB are cyclic, so this angle, the angle CFD equals to this one, angle HBD, right? HFD equals to HBD. And also HBD equals to HAE, right? Angle HBD equals to angle HAE because these two are equal, and this is 90 degrees, this is 90 degrees, so these two are equal. And because AFHE are cyclic, so angle HAE equals to angle HFE, right? Then we got that angle DFC equals to angle CFE, right? So these two are equal, means that AD is angle bisector of angle FDE, and CF is angle bisector of angle DFE, and H is intersection point of the two angle bisectors, which means that H is in center of the triangle FDE. Okay, so that is saying the orthocenter is the in center of the pedal triangle. This is a pedal triangle, right? And the next part is that for all the inscribed triangle in an acute triangle, the perimeter of the pedal triangle is the shortest. To prove that, we first consider about how can we find. So let's say we have 2 points here, right? Call it A and B, and we want to. There is another line. It's L. We want to find a point on the L. Make the parameter a point on the L, let's call it P, right? So make the parameter of triangle PAB to be the shortest. How can we find this P point? The idea is that we can think about the physics. The light goes the shortest path, right? And if a light hit on the L is a mirror, then we know that we would have the angle AP, let's call this as I don't know, X and Y. Okay, the angle APX should be equal to angle BPY, right? That's the point P. And how can we find that P? We find the symmetrical point of A to the line L, so which is here. Let's call it A prime. And then we connect A prime to B, right? The intersection would be the points that we are looking for. Let's now call this point as P, okay? So we can prove it, right? Because AA prime is perpendicular with line L, right? And we can find the perpendicular line of the line L passing through P, right? So let's call it line T, okay? So we know that line T is actually in parallel with A prime A. That means this angle equals to this angle, right? Because these two are in parallel. And because A and A prime are symmetrical to the line L, that means this angle equals to this angle. And we already know that line T is in parallel with line A prime A, so this angle, the angle BPT, equals to this angle, right? Angle A prime. Then we see that this angle equals to this angle. That's for the light, right? And this point should be gives the shortest parameter of triangle PAB. Why? AB is constant point. AB are constant points, right? That means the distance from A to B is constant, right? The only thing that we can change on the figure is the position of P, and it changes the distance from P to A and P to B, right? So in this case, that PA plus PB equals to A prime B. And if you find any other point, let's say here, right? This is another point, let's call it P1. The P1 point, so P1A plus P1B equals to P1A prime plus P1B. That is larger than A prime B, right? Because P1A prime B form a triangle. So P1A prime plus P1B larger than A prime B, right? That is saying the P points that we found gives the shortest parameter of the triangle PAB. Okay, similar idea we can use here. That is saying in the triangle ABC, let's just fix the altitude foot D and E, right? And we are looking for another point on let's call it P, on the AB, which can make the triangle PDE has the shortest parameter, right? And the solution would be same as this one. We just find the symmetrical point of D to AB. Let's call it D prime here. And then we connect DE, and DE intersect AB on another point. Let's call it F, right? So the question is that whether CF is passing through the orthocenter H, right? That's the question. We already know that the way that we find this F should be give the shortest parameter, right? Okay, so to prove that CHF are collinear, we actually can do this way. We first find the let me redraw the figure. This is not one. Right, this is better. So A, B, C, D, E. We find the symmetrical point of D to AB. So let's call it D prime. Okay, we just hold it there and consider about the foot F. Okay, we connect D prime F and we connect FE. There is nothing guarantees that D, F, E are on the D prime FE are on the same line, right? I didn't draw like that. Now we just think about angle D prime FB equals to angle DFB, right? These two are equal, right? These two are equal. And we already know that angle DFC equals to angle CFE. And angle DFC plus angle BFD equals to 90 degrees, right? That means angle D prime FB plus angle DFB plus, so this angle plus this angle plus this one plus angle DFC plus angle CFE. See, because this one equals to this one equals to this one, and because these two, the sum of these two angles equals to 90 degrees, that means the summation of these four angles equal to 180 degrees, right? That is saying D prime F E are collinear. We already know that 2 points can define a line. So this line can be defined by D prime and E, right? And F is on the D prime E, and F is also on AB. That is saying that when we're looking for the shortest parameter of the triangle FDE, we draw the symmetrical point of the D to AB on D prime, right? And we connect D prime E. Then the intersection point F is also the foot of the altitude on edge AB, right? So it's saying that when we have the foot here, that's guarantees the shortest distance of the FD plus FE if DE are fixed, right? Okay, now we just let it, only point D is fixed. Right, if we only let the point D to be fixed, we can do the similar thing. We just find D here, A here, B, C. So this is D prime, right? And we can do D double prime. And then we just connect the D prime to D prime prime. And we call this point as F, this point as E. We say that this gives the shortest distance, actually shortest parameter of the triangle FDE, right? Because it's a distance from D prime to D prime prime, right? That's the shortest distance. No matter what combination of the point you can find on the ABAC other than FE, it's always form a triangle that makes a summation of the FD plus FE plus DE larger than or longer than D prime to D prime prime, right? So this would be the shortest, and we can still use a similar method to prove that CF and BE actually are the altitude of AB and AC. Just use a similar method. We use it first, and then we just prove that D prime prime, and E on the same line. Similarly, D prime, D prime prime, and F are on the same line. We just need to prove that. Okay, I'll just leave it here. And for the next point that we allow point F, point E, and point D can be moving around, so we can still fix a point D. It not necessarily to be the altitude here, right? We just fix a point D here, then the method would be the same that we use this method to find it, and then we fix the points that we find of the F and E, and then we're looking for the point D. We would eventually come close to that AD should be perpendicular with BC. Okay, so I'll just stop here. That's for the property 11. Let's see the property 12. Right, property 12 is saying that the three edges of the pedal triangle are in parallel with the tangent from vertices of original triangle to its circumcircle. So this is a circumcircle, this is a center, and we draw the triangle here, A, B, C, and we want to find the D, E, F here, and we know that this is a pedal triangle, and if we just do, this is kind of symmetrical, right? We prove one point, then others are the same procedure. So we want to prove that this line L is in parallel with FE, right? So we actually can do this. This angle equals to this angle, right? The angle, let's give some name here. For example, a point X and a point Y, right? So the angle BAX equals to, right? The angle BAX equals to angle BCA, right? And we know that angle AFE plus angle CFE equals to 90 degrees, right? So this angle plus this angle equals to 90 degrees. And because AFHE are cyclic, that means angle CFE equals to angle CAH, right? This one equals to this one. And we know these two, the sum of these two is 90 degrees, and the sum of these two is 90 degrees. That means angle AFE equals to angle ACB. And angle ACB is angle BCA, right? And it equals to angle BAX, right? So AFE, this angle, equals to BAX, equals to this angle. That means L is in parallel with FE, right? So similarly, you can find that the tangent from point C is in parallel with DE, and the tangent from point B is in parallel with FD. Okay, that's property. That's a property 12, right? Let's see the property 13. Okay, property 13. Let me find the clean set. Okay, property 13 is saying that H is orthocenter of an acute triangle if and only if. So H is the orthocenter of an acute triangle if and only if HA times HB times AB plus HB times HC plus BC plus HC times HA times CA equals to AB times BC times CA, right? So we just prove the case that H is orthocenter first. A, B, C, H, D, E, F. We already know that HA. So we want to prove that HA times HB times AB, right, plus HB times HC times BC plus HC times HA times CA equals to AB times BC times CA, right? So for this problem, actually, let me draw the circumcircle here. Okay. We can connect the BO and extend it to J here and AO to K here and CO to let's call it L here. Okay, so we know that HA, because we did the extension, right? So we know that JC equals to AH and AJ equals to HC, right? And we know that AJCB is a cyclic quadrilateral, right, inside of the circle O. So we can do the Ptolemy theorem that AJ times BC plus JC times AB equals to BJ times AC, right? And we know that AJ equals to CH, so we got CH times BC plus JC equals to AH, so AH times AB equals to BJ, that is 2R times AC, right? So we just reform this equation to the next one, and then we can have BK equals to CH, CK equals to BH. So for A, B, K, C, we can have, let's just mark this one. Okay, we can have BK times AC plus KC times AB equals to AK times BC, right? And BK equals to CH, so CH times BC, CH times AC, right? This is AC, CH times AC plus KC equals to BH, so BH times AB equals to AK, AK is 2R times BC, right? Let's mark this one. And for ALBC, okay, ALBC, we know that AL equals to BH and LB equals to AH, right? So in ALBC we have AL times BC plus LB times AC equals to AB times CL, right? And AL equals to BH, so BH times BC plus LB equals to AH, that is AH times AC equals to CL, that is 2R times AB, right? we have these three equations here. So consider that we have HC times BC here, and we have HB times BC here. So we do half of HB in the first equation, we do half of HA in the second equation, we do half of HC in the third equation. Then we can have a new set, right? The new set would be half of HB times HC times BC plus half of HA times HB times AB equals to 2R times half of AC times HB, right? And for the second one, we have half of HC times HA times AC plus half of HA times HB times AB equals to 2R times half of HA or AC, actually BC, right? BC times HA. And for the third equation, half of HB times HC times BC plus half of HC times HA times AC equals to 2R times half of AB times HC, right? If we sum these three equations together, we can see that we have half of HB, HC, BC, we have half of HB, HC, BC, that make them HB, HC, BC, and we have half of HA, BA, HA, HB, AB here, half of HA, HB, AB here, makes them full of HA, HB, AB, and we also have half of HC, HA, AC, half of HC, HA, AC, makes them full of HC, HA, AC. So then we got HA times HB times AB plus HB times HC times BC plus HC times HA times AC equals to 2R times half of AC HB plus half of BC HA plus half of AB HC, or it equals to R times AC times HB plus BC times HA plus AB times HC, right? And look at the right side. So the left side of the equation are the same, and we want to prove that the right side would be the same. Then we just prove this is true, right? So what about the AB times BC times CA? What is it? AB times AC times BC. BC can be rewritten as 2R sine angle BAC, right? So this equals to half of AB AC sine angle BAC times 4R, right? So that equals to 4R times the triangle area of ABC. That's a production of ABBCCA. And how about this side? Can we prove that this one to be the 4 times of the triangle area, triangle ABC area? So let's see. AC times HB. AC times HB. Because HB equals to KC, and we know that AK is a diameter, so angle ACK is 90 degrees. Actually, because AL is in parallel with BH and in parallel with KC, and also AL equals to BH equals to KC, so we know that ACKL is a rectangular because this is also 90 degrees. So that means AC times BH equals to AC times KC equals to the area of rectangular ACKL, right? And Then we know that ACKL is a rectangular, and we know the area. We notice that the area of ACKL is actually 4 times of the triangle area AOC, right? That makes the first term to be 4 times of triangle area AOC. Similarly, for the BC times HA, that equals to BC times CJ. So that is 4 times of the area of triangle BOC. And for AB times HC, right? HC here equals to AB times AJ, right? AB times AJ, that's 4 times of the area of triangle AOB. 4 as AOB. And now we see that AOC plus BOC plus AOB, the area would be triangle ABC area. So it equals to R times 4 times the triangle area of ABC. Then we can see they are equal. Okay. Oh, I may miss this part for you. So AC times HB. AC times HB, that's equals to AC times KC. So that's 4 times of triangle area AOC. Right, I just write it down here. Then we add the AOC, BOC, AOB together, that's the triangle area of ABC. And then we know these two are equal. So we just prove that this equation is valid, right? Okay, now we want to prove the other case. The other case is saying that if, okay, the other case is saying that if this equation is valid, then we want to prove that H is orthocenter, right? If this equation is valid, we want to prove that H is orthocenter. So we have a point H here, A, B, C. We know that HA times HB times AB plus HB times HC times BC plus HC times HA times CA equals to AB times BC times CA. Right, we know this is true, and we want to prove that point H is orthocenter, right? So the way we can do is that we do the connection of HC first. Okay, we connect HC first, and then we do a parallel line of HC passing through point B. Okay, and we do a parallel line of BC passing through H. Basically, we just use HC and BC to form a parallelogram here, right? Let's call it D. So that is HCBD. That's a parallelogram, right? And DH equals to BC. So we have HCBD. Do this, and then we can connect the AH, right? And from the AH, we can form another parallelogram, right? Let's call it E. So do parallelogram AHDE. And then we connect EB. Notice that DH equals to BC. So DH actually in parallel and equals to BC, and in parallel equals to EA. So we know that AC BE is a parallelogram, right? ACB is a parallelogram as well. Then we connect AD here. Connect BH here. Okay, now let's think about the, we know that ED equals to AH and EA equals to DH, right? And DB equals to CH. We just have that BH, there's nothing equals to BH, right? We just have this one hang out there. So in AEDB, we can use Ptolemy, general case of the Ptolemy theorem in any quadrilateral, right? So we get ED times AB plus EA times DB larger or equals to EB times AD, right? And we know that EB equals to AC, EA equals to BC, and ED equals to AH. So we replace it. AH times AB plus EA, that is BC, times DB. DB equals to CH. So let's see, HC. And it's larger or equals to EB, which is AC, times AD, right? And in ADBH, we can still use the Ptolemy theorem. So we have AD times BH plus DB times AH should larger or equals to AB times DH. So this one we can rewrite it as BH, so HB times AD plus DB is CH, right? So CH times AH larger or equals to AB times DH. DH is BC, so AB times BC, right? We got this one. So if we look at the first one here, we have AH times AB plus BC times HC larger equals to AC times AD, right? We compare this one to the target one. We have AH times AB here. We just don't have the HB, right? But we have BC times HC here. We don't have HB here. So we can just times HB in the left and right side of the inequality equation. Then we have HA times HB times AB plus HB times HC times times BC larger or equals to, I'll just write it here, AC times HB times AD, right? And then we can put the third term into it. So we have AH times HA times HB times AB plus HB times HC times BC plus HC times HA times CA larger or equals to AC times HB times AD plus HC times HA times CA, right? So we have CA here, we can extract it out. Then we have, so this one equals to AC times HB times AD plus HC times HA, right? We have HB times AD plus HC times HA. We know that HC times HA actually equals to DB times HA, right? So it equals to AC times HB times AD plus HC times, no, HC is DB actually, so HA times DB. Right, we have it here. So let me see. So see this one, comparing this one to this one. It is also larger than AC times, we replace this, right? HBAD and AHDB. DB is CH, right? DB is CH. So that's CHHA. We replace this one by this one, right? So that is by this one. That is AC times AB times BC, right? So we get that in a general case, this one, the summation of this one should be larger or equals to AC times BC times AC, right? And the equality only valid when A, E, D, B are cyclic and A, D, B, H are cyclic, right? So equality exists only if A, E, D, B are cyclic and A, D, B, H are cyclic, right? They're cyclic, then we can have this equal equation here. That means we already confirmed that this is valid, right? This is a problem set. So we know that AEDB are cyclic and ADBH are cyclic, right? So now we think about how can we prove based on this. Based on this equation, we just get the two conclusions here, that AEDB are cyclic and ADBH are cyclic, right? So basically, we want to use these two conditions, the conclusions that we get from the equation. We want to prove that AH is perpendicular with BC and BH is perpendicular with AC and CH is perpendicular with AB, right? That's the case. Could be the orthocenter. So think about that AEDB are cyclic and ADBH are cyclic. That means AEDBH are cyclic, right? So we got AEDBH are cyclic. So AEDBH are cyclic. That is saying we have ED equals to AH. Let me see. So it's actually asking us to put, because let's consider about this case. So if DH is, so if AH is perpendicular with BC, because DH is perpendicular with BC, that is saying we need to prove that angle AHD is 90 degree, right? If angle AHD is 90 degree, then AEDH is a rectangular, right? So that is saying we need to prove that the angle AB, so because AHD need to be 90 degrees, then the angle ABD need to be 90 degree, and angle angle AED should be 90 degree, right? So how can we do that? We already know that H is a point, and these 5 points are cyclic. Let's see. That means this angle equals to this angle equals to this angle, right? And also we know that this one equals to, oh, okay, see? Because because AEDH is a parallelogram, right? Because AEDH is a parallelogram, so the angle AHD equals to angle AED, right? This one equals to this one. And because AHBD also are also cyclic, it is a cyclic quadrilateral, so the angle AHD equals to angle okay, that's actually enough, right? These two angles need to be equal, and it's a cyclic quadrilateral. That means the AD, the chord AD, has a two angle. You know, the sum of these two angles should be 180 degree, and they are equal. So each one should be 90 degree. That means AH is perpendicular with DH, which means AH is perpendicular with BC. Right, AH is perpendicular with BC. And also, we want to prove that BH also perpendicular with AC, right? And AC is in parallel with EB, right? So because this is a rectangular, you cannot think it as just a parallelogram. This is a rectangular, so AD would be the diameter and the EH would be the diameter. That means this would be 90 degree. So EB is perpendicular with BH and EB is in parallel with AC. So BH is perpendicular to AC, right? So we also got BH is perpendicular to AC, which means that AH is perpendicular to BC and BH perpendicular to AC. So we got H is orthocenter. Okay. So this just looks like a property, but this actually a problem from the China the China Olympic competition, like the national competition, CMO. I forgot which year it is, but it's from the CMO actually. Okay, that's a difficult one, but we just prove it. Now let's see the property 14. Let H be the orthocenter of a non-right triangle ABC. D, E, F are feet of altitudes. H1, H2, H3 are the orthocenters of triangle AEF, triangle BDF, triangle CDE, respectively. Then we want to prove this. Okay, let's just draw the figure here. A, B, C, right? And this is D. This is E. This is F. So we know that H1 is the orthocenter of triangle AEF. So we connect to EF, connect to ED, connect to FD. We want to find H1, which means that from A, we do the perpendicular line to FE, and from F, we do it here. Right, that is, so this is H. That is H1. And H2 is orthocenter of triangle BDF. So that is H2. And H3 is orthocenter of triangle CDE. Okay, so this is H3. And we want to prove that triangle DEF is congruent to triangle H1, H2, H3, right? So H1, H2. So we want to prove that triangle DEF is congruent to triangle H1, H2, H3, right? I draw these lines. Looks like very complex, but they are very useful, right? Because if we just mark the foot here, on all these edges I, J, K, L, M, N, right? So we know that EM is perpendicular with AB, right? And also DN is perpendicular with AB. We know that CF is perpendicular with AB. So we have EM in parallel with CF in parallel with DN, right? And similarly, we have FI in parallel with AD in parallel with EJ. Also, we have DK in parallel with BE in parallel with FL, right? So we have all of these lines are in parallel. So we know that DK is in parallel with FL, right? So this line is in parallel with this line. And we know that EM is in parallel with DN, right? This line is in parallel with this line. And we know that FI, this line, is in parallel with this line, right? EJ. So this is in parallel with this one. Right, this is in parallel with this one. So see here, FH1 is in parallel with DH3. So we actually get FH1 in parallel with DH3. FH1 in parallel with DH3. And also FH2 is in parallel with EH3. And we have EH1 is in parallel with DH2. Right, so this line is in parallel with this line. This line is in parallel with this line. So we already know that angle FH2D equals to angle H1EH3. Right, that is true for all other angles. So angle FH2D equals to angle H1EH3. And angle FH1E equals to angle H3DH2. So this one equals to this one. This angle equals to this angle and this angle. Angle DH3E equals to angle H1FH2. Right? Right. So now the question is that how can we prove the triangle FDE is congruent to triangle H1, H2, H3, right? So think about that, the way that we can prove the two triangles are congruent. In this case, we can have two choices. We can first prove that triangle DEF is similar to triangle H1, H2, H3, and then we find either one side, right, of the triangle H1, H2, H3 equals to the equivalent or reference to one side that in triangle DEF they are equal. Then we just prove they're congruent. All just think about another way, because H1, H2, H3, they are kind of symmetrical. So actually, when we prove one side are equal, we basically prove that all of the sides of the H1, H2, H3 are equals to the sides of the triangle DEF respectively, right? So if we want to prove that, we want to prove okay, now look at this one. I mean, we just want to prove that they're all equal. So here, HD is also in parallel with FH2, right? HD is in parallel with FH2. And also DH2 is in parallel with CF, right? DH2 in parallel with HF. So we got FHDH2 is a parallelogram, right? It's a parallelogram. That means HD equals to FH2. HD equals to FH2, right? So this one equals to this one. And similarly, because HD is perpendicular with BC, EH3 is perpendicular with BC, so HD is in parallel with EH3, and also DH3 is in parallel with HE, that we know DH3 is a parallelogram. So we know that HD equals to EH3, right? Which means FH2 equals to EH3. FH2 equals to EH3. So these two are equal. And now we know that FH2 is in parallel with EH3 and they are equal. So FH2H3E is a parallelogram, right? It's a parallelogram. That means FE equals to H2, H3, right? We just prove one side, corresponding sides are equal, and we know that it's kind of symmetrical. We can rotate the ABC and H1, H2, H3, so we know that all of them are equal. So we got triangle DEF is congruent to triangle H1, H2, H3. Okay, so that's for the first part, and we have several corollaries here. So the corollary one, triangle H1EF, triangle H1EF, H1EF is congruent to triangle DH2H3. We actually already proved that, right? Because because H2H3 equals to FE, and also because FH1 is in parallel with HE, right? Actually FH1 is in parallel and equals to HE, in parallel equals to DH3, right? So these two are equal, these two are equal, these two are equal. So that means triangle FH1E is congruent to triangle H3D H2, right? And other parts are the same. And for the second corollary, it's saying that the area of H1F, H2D, H3E is twice of triangle H1, H2, H3, right? So the area of these, because we already know that triangle FH FH1E, the area of triangle FHE is congruent to triangle DH2H3, right? So yeah, actually, these three, we want to prove that equals to H1, H2, twice of H1, H2, H3. So yeah, if I write it down, it would be easier to see. Let me. So we want to prove that the area of H1 FH2 DH3E equals to twice of the triangle area of H1 H2 H3, right? So the area of triangle H1 H2 H3 equals to triangle area of triangle area of H1, sorry, DEF plus DEF plus area of triangle FH1E plus area of triangle DH3E plus area of triangle FH2D. Right, so we want to prove that's this one. So let's just remove this out first. We know that the area of H1F, H2D, H3E can be calculated as this area plus this area plus this area plus this area, right? And we know that area of FHE, because FH1EH is a parallelogram, so the area of triangle FH1E equals to the area of triangle FHE, right? So it equals to triangle DEF plus triangle FH1E, that is FHE, plus triangle DH3E, that is DHE, plus triangle area of FH2D, that is FHD, right? And we know that FHE plus DHE plus FHD, that is the area of triangle DEF, so it's twice of area of triangle DEF, and it equals to twice of area of triangle H1, H2, H3. Okay, that's this one. And we have corollary 3, saying that HH1 and EF, HH2 and FD, HH3 and DE bisect each other respectively. Okay, so HH1, FE bisect each other, of course, because FH1EH is a parallelogram. HH2 and FD bisect each other, yeah, because FH2DH is a parallelogram. HH3 and DE bisect each other because HDH3E is a parallelogram. Okay, so we just go over all of the properties of the Orthocenter that I collected. We will see more when we discuss about the problems. I think the property of, because the Orthocenter is a very important, it is very important. Especially it correlates with other centers such as circumcenter and incenter. We have tons of problems here, so we need to be very careful of the Orthocenter. And I hope you like this video. We will discuss about the problems later. Thank you. See you in next one.